This problem starts out by saying that this circular blade on this saw is turning at a certain rate. Let's call that omega naught. It's different for everybody, so I'll just call it omega naught. At the instant the motor is turned off, it's going this fast. In 19.4 seconds, that's what it says for me, but in some time t, the speed of the blade is reduced to some other speed, which I'll call omega. All right, so that's the order that the numbers appear in your problem. First they talk about omega naught, then they talk about the time, and then they're talking about omega. See that? And they're all in the right units. Omega naught is in radians per second. That's the right units. Time is in seconds. That's the right units. And omega is also in radians per second. So those are all the right units that we like to use. It says, assume the blade to be a uniform solid disc of radius something, which they give in meters, which is the right units, and a mass of, I think everybody has 0.400 kilograms. That's the right units too. All right. And they ask you to find the magnitude of the net torque. So the question here is torque. Well, at this point, you only have one equation for torque, and that's torque equals I, moment of inertia, alpha. So in order to calculate the torque, we need to know the moment of inertia and the angular acceleration, but they told us neither one. So we're going to need to calculate both of those in order to be able to do this. So let's start with the moment of inertia. The moment of inertia, we always look at our chart or our list of equations to find out what the right equation for this is. And it says, assume the blade to be a uniform solid disk. So that's the solid disk formula, 1/2 mr squared. So as long as we know the mass and the radius, we can calculate this. And look, there they are, mass and the radius. We calculate that. I'm not going to do it because your numbers are different. So now, assuming you've done that calculation, we have I. And now we need to find angular acceleration alpha. So we think about, well, where could we find alpha? It's in this equation, but this is what we're trying to use. We can't use this equation to find alpha, so we need to find alpha from somewhere else. One possibility is that the tangential acceleration is equal to alpha r, but that's not going to help us because we don't know the tangential acceleration. So I guess we have to go to rotational kinematics. So we look at all of our rotational kinematics equations, and of course I like this one best because it's the easiest. Omega equals omega naught plus alpha t. It doesn't have any squaring in it. It doesn't have that many terms in it. It's the easiest. I like it. It does have alpha in it. That's good. So as long as we know omega and omega naught and t, we could find it from this equation. And look, we do. So we can solve this for alpha. That's omega minus omega naught over t. We can't make anything equal to 0 because they're not 0. But we can calculate alpha from here. And then, let's see if I can change colors. Then we can take this and stick it in here. And we can take this calculation and stick it in here. And finally calculate the torque. And because everything was in the right units to begin with, the torque is going to come out in the right units.